Okay, hello everyone. Good morning. Uh, that's it. Last class of the semester. We're only gonna have the final left, and um, let me start talking about that. So, as I was telling you last class, now it's been settled that the final exam will be 48-hour time period, and you are going to have to upload one file per problem. So it will have different assignments for different problems. It's not set up yet, so I cannot really show you or link like I said I would probably do from our Canvas site, because it's not set up yet. But once it's over there, you can find a link from our Canvas page taking you there. Make sure that you have accepted your invitation for the Math 150B resources page, because that's the overall page in which everyone will take the final exam. And other than that, it will be the same format. It will be available at the regular time that it was scheduled, and you will have 48 hours to complete it and upload your files, which you can you can do revisions, right? You can upload and then upload later if you found out that you had a little mistake or you wanted to improve your solution. You can do that, and that's gonna be it. It will probably take a while to be graded because it's gonna be graded collectively, but all of us professors from 150B. So each one of us will grade one problem. So I'm only going to grade one problem for all the sections. So and your grades will not be ready until every one of the professors does their job, right? Grades their individual problem. But eventually you will find out about it, and your grade will be posted on our Canvas site. Good. So we were reviewing for the final exam, and we're looking at the problems from our review sheet. And I also made this list of the overall topics, and I have been putting check marks to the ones we've covered already. Last time we talked about a known power series, and we also did problems about the radius and the interval of convergence. So we'll pick it up there today. We'll do Taylor polynomials and Taylor series, which are in a sense related. And then we'll move on to chapter 12, all right? So let's get to it. Let's go to the list of problems. If you have any specific ones that you would like to know, please feel free to put it on the chat area, or to just let me know that there's a problem that you would like to see. Don't just wait, because we may simply not get to it. All right, so this is where we left off last time. So now it says, so we have these types of problems about, well, using power series and also Taylor series. We also left this one earlier, which was about Taylor polynomials. So maybe we can do a little bit about this one. It says, find the quadratic approximation, the second order Taylor polynomial, and then use it to approximate the given value. Right? So let's pick one here about C. C sounds like a good one. The function is arc tangent x at 1 and approximate arc tangent of 2. Okay, so easy, and the same formula applies both for Taylor polynomials and for Taylor series. So I'll write it here. In general, the nth Taylor polynomial is given by this. Is the k derivative evaluated at a over k factorial x minus a to the k. And you go from 0 to n. That's the Taylor polynomial of order n. And if you want the Taylor series, then you simply go all the way to infinity. And that's the Taylor series. Okay, so here the center is 1. So it's tempting to want to use the known power series we know for arctangent. So we know this one, that arctangent of x is, in fact, this one over here is -1 to the k x to the k over 2k plus 1. I'm doing this right. Let me see. So we got this one from, yeah, it's correct. Yeah. So we know this one, right? It's one of those that we should know. So this is, maybe it's x plus 1. Let me see. It's x plus k plus 1 here. So it's x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7. So we go over the odd numbers and we alternate signs. So we know this one, but we cannot use this one because this one is centered at 0. And look here, the center is 1. So there's really no going around this. We need to do the work. All right. Now, the good thing is we only need the Taylor polynomial of order 2. So we only need to go to the second derivative, right? So that will be easy. So the best way I recommend for you to do these problems is to do a little table, right? So here's the table that I will set up. So I put the case over here. I'm going to need 0, 1, and 2. Then I need to figure out what's the kth derivative of x, and then figure out what is the kth derivative when we plug 1. Now, the original function is arctangent. And arctangent of 1 is, well, pi over 4. Then the derivative of arctangent is 1 over 1 plus x squared. And when we plug 1, we get 1/2. And then the derivative of these, that's like 1 plus x squared to the power -1, is minus 1 plus x squared to the power -2 times 2x. So in other words, is -2x over 1 plus x squared squared. And when we plug 1, we get -2 over 2 squared. So that's -1/2. So that's it. That's all we need, right? Once you have these, you can go back to our recipe and just plug the things in. So here is P2. From 0 to 2, k derivative at 1 over k factorial, x minus a to the k. So what is it? The first one is pi over 4, pi fourths. Then first derivative is 1, so it's 1/2 x minus 1. And this should be 1 already. We know that a is 1. We put it in here. And last term is -1/2, so it's -1/2 over 2 factorial, x minus 1 squared. So altogether, this is 5/4 plus 1/2 of x minus 1 minus 1/4 of x minus 1 squared. And that's the answer of the first part. Now, how do you use it to approximate arctangent of 2? Well, this function approximates arctangent. So arctangent of x is approximated by P2 of x. So in particular, if I plug the number 2, so arctangent of 2, similar to P2 of 2, and when I plug 2, I get this. 2 minus 1 is 1, so that's 1/2. 2 minus 1 is 1, so that's -1/4. 1/2 minus 1/4 is 1/4, so this is pi minus 1 over 4. That's the approximation for arctangent of 2. All right, so that's the end of this problem. Let's go back to the other ones in the list. So the others are done similarly. They're all pretty straightforward. You just need to calculate your derivatives carefully and plug the numbers, right? There's really not much to, not many ideas there. Now let's go over here. So these are similar. Let's take now a look at 22. These are similar, but now you need to do the, well, okay, it says find the first four non-zero terms. The first four non-zero terms is kind of like doing, well, not exactly P4, because maybe some of them are zeros, but if none of them are zero, then it's like doing P4, right? So this is similar, except some of these are easier because you can perhaps use the ones that we know already, right? Not precisely because the centers are different, as you can tell here. This one, the center is pi over 4. For C, for B, the center is 4. And for A, it's not a function that we know for the known Taylor series, all right? But other than that, you do them the same way. So let's pick one here. Maybe let's try C. So we want to do the Taylor series for the function sine 2x, centered at pi over 4. Here we go. So here is the Taylor series definition, is the k derivative at a over k factorial x minus a to the k, from 0 to infinity, right? So again, we're going to need the derivatives and plug them in pi over 4. So let's start creating a table. So here's k derivative at pi of x, and then k derivative at pi over 4. The original function is sine 2x, and when I plug pi over 4, I get sine of pi over 2, which is 1. That's nice. First derivative, the derivative of sine, what is it? It's cosine, and then times the inner function, so it's 2 cosine 2x. And when I plug pi over 4, I get 2 cosine pi over 2, and the cosine of pi over 2 is 0. So that one doesn't count, right? Because we need to find 4, but 4 non-zero. So this one doesn't count. So we only have 1 so far. Second derivative. There is going to get another 2 here. The derivative of cosine is negative sine. So now it will be negative 4 sine 2x. And when I plug pi over 4, it will be negative 4 sine of pi over 2. So that's negative 4. Okay, we got 2. And we go the third derivative, and the third derivative will be now another 2, so negative 8 cosine 2x. It will be 0 because cosine of pi over 2 is 0, so that one doesn't count. We keep going. The fourth will be the derivative of cosine is negative sine, so this is now 16 sine 2x. And when we plug pi over 4, this is 16. So we have 1, 2, 3. We need one more. This will be 32 cosine 2x, and this will be 0. Still doesn't count. And then negative 64 sine 2x. And when we plug it, we get negative 64. And I kind of see the pattern now, right? If I wanted more than 4, we could figure it out. Because look, it's 1, 0, negative 4, 0, 16, 0, negative 64. Yeah, so it's kind of easy. These are powers of 4. This is 4 to the first power, 4 to the second, right? This is 4 squared. And this is negative 4 cubed. So it alternates signs, and we go by powers of 4. This is 4 to the 0 if you want. So it's not that difficult, but we're not going to overcomplicate it. We only need 4. So what are the first 4 non-zero terms? We have the first one was 1. So it's 1. Then the second one is negative 4. So it's negative 4 over 2 factorial x minus pi over 4 to the second power. Then the third one is 0. The fourth one is 16. So it goes plus 16 over 4 factorial x minus pi over 4 to the 4th power. Then the fifth one is 0, and the sixth one is negative 64. 6 factorial x minus pi over 4 to the 6th power. All right, and then dot, dot, dot. So there are more, but they didn't ask us to do that. We could, right? Like we figured out the pattern, right? So really the pattern continues like that. So in general, it's going to be like, well, I'm not going to do it. It's not just, there's no point in doing it. The problem only asks for the first 4. We only do the first 4. And I doubt that they will ask you to find a general one, because sometimes the patterns are just very, very hard to get. Okay, so let's move it along instead. So we have more things to do. We can now use power series to evaluate things that we couldn't do before, and that's an example of this would be like this 23rd. And we had a problem like this in our exam, and most of you did it quite successfully. So let's do it. So for example, 23a, we want to integrate from 1 to 2 sine x over x. This function, by the way, you cannot integrate it with by parts, use substitutions. None of those things will work. It's one of those that cannot be written in terms of elementary functions. So this is where the series are very successful. We can go around it by using series, right? So what is the series we want to use? We want to use the series of sine x, which is this one. Negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1 factorial from 0 to infinity. In other words, this is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, etc. So we go on the factorials, odd ones, alternating signs. Okay, so then you do sine x over x. Oh, and the convergence is everywhere. This is a good one about this one. This is true for any x. So then we divide by x, and then what we get is negative 1 to the k, x to the 2k. So we cancel this 1, right? In other words, this is 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial minus x to the 6 over 7 factorial, etc. So now these numbers, we subtracted 1 to the exponent, right? And the good thing is that now we can integrate. So if we integrate sine x over x from 0 to 1, we can simply integrate term by term. It will be the integral from 0 to 1, term by term of these. It looks ugly, but yes.
Wasn't it from 1 to 2?
Yes, thank you. That matters because that 0 is not defined, right? This function. Well, it kind of is, but it's an improper integral. Yes, 1 to 2. Thank you. Yeah, that's considerably better. These guys are constants. We can take them out of the integral. And now the integral is not so hard. It's just x to the 2k. And that's easy to do because you just add 1 to the exponent and divide by the new denominator, right? So this is, I'm just copying the sum, the constants that we took out. And now, like I said, it's x to the 2k plus 1 divided by 2k plus 1 from 1 to 2. So this becomes 0 to infinity, negative 1 to the k, 2k plus 1 factorial, 2 to the 2k plus 1, minus 1 over to the 2k plus 1 divided by 2k plus 1. And that's it, right? I mean, it's a weird series, but whatever this series is, that's the answer to that integral, right? And you can take a few terms of this series to approximate it if you wanted to, but that's the answer, right? It's not pretty, but that's what we were requested to do. In fact, I think it only says, here it says estimated using the first two non-zero terms. So you could just use the 0 and the 1 term to estimate it. But in our exam, I ask you for the entire thing. So it's good to know the entire thing. In the final exam, maybe you get asked to find the entire thing as well. Great. So that takes care of chapter 11. And now we can move on to chapter 12, which is the one about, we had the following things: parametric curves, with polar equations, and all the calculus with polar graphs. So the slopes of tangent lines of polar graphs, the area of polar curves, and the arc length of polar curves, right? So now let's do some problems regarding that. Starting with these ones, find the tangent line. So how do we find the tangent line if we have a parametric equation? And here's what you need to remember. It's actually very easy. What you need to remember is that the derivative if you have a parametric equation, x is f of t and y is g of t, then the slope we know is the derivative of y with respect to x. And we found out that there's a very easy way to do this. Is just do the derivative of the y part divided by the derivative of the x part. In other words, g prime divided by f prime at the point where you want them, right? So that's all we need to do problems like this one. So let's take a look at the first one here. The first one here says, what if we have, or the second one that looks a bit more, a bit harder. So for part B, so 25B, we have that x is ln t and y is arctangent of t. And we want it at t equals 1. What is this? The tangent line. So find the tangent line. So we need the slope and we need a point. We have the slope with what we just outlined here. This is how we get the slope, and the point, you just get it by plugging 1. You get the x and the y. So let's do that first. So if t is 1, x is ln of 1, which is 0, and y is arctangent of 1, which is pi over 4. So the point is 0 pi over 4. That's the point. And what about the slope? Well, the slope will be dy dt divided by dx dt at t equals 1. What is the derivative of y? The derivative of arctangent, that's 1 over 1 plus t squared. The derivative of ln t is 1 over t. And when t is 1, this is 1/2 divided by 1. So that's 1/2. So the slope is 1/2. And you have a slope, you have a point, you have the equation. So here's the equation. Y minus pi over 4 equals the slope times x minus 0. Okay, so that's how it's done. It's really easy. Any of these problems. So getting the slope is actually quite straightforward. Okay, so let's move it along. I'm purposely skipping the parts that I don't think will be on the final exam because they're not that irrelevant, like or you know, they're not really hard at all, and I'm concentrating on the ones that I know for sure they will be there. So for sure, I think there will be a problem like the one we just did, either for a parametric curve or for a polar curve, right? So we'll get to do the polar ones here. So here's the next one. So it's the same type of problem, but now for a polar curve, right? And let's do B, for example. So this one over here. So 27 part B. This time R is 2 sine 2 theta, and we wanted a theta equals pi over 4. And here you need to remember what is the other formula, the formula for the slope with polar equations. So let's review that first. So for polar equations, well, for polar equations in general, you have the following. You have that R is f of theta. And then you need to remember how you can get x and y. Well, x is usually r cosine theta and y is r sine theta. That's how we go from polar to rectangular. But r is f, so this is f cosine and this is f sine. So then if you want the slope, the slope will be dy d theta over dx d theta. The derivative of this with respect to theta is product rule, f prime sine plus f cosine. And the derivative of x with respect to theta is f prime cosine minus f sine, because the derivative of cosine is negative sine. So I never memorize the formula, right? But if you want, you can simply take a look, and this would be the formula, right? And I just explained to you where the formula comes from. We did it in class, and I just did it right now. So this is how you get the slope. So that's what we need to do for this particular problem. In this particular problem, the function is 2 sine 2 theta. So you just need to calculate everything here. So what is it? The derivative of 2 sine 2 theta times sine theta plus 2 sine 2 theta times cosine theta divided by the derivative of 2 sine 2 theta times cosine minus 2 sine 2 theta times sine. And now we need to simply evaluate these numbers, right? What is this derivative? This is, it will be 4 cosine 2 theta times sine theta plus 2 sine 2 theta times cosine theta in the top. And in the bottom is 4 cosine 2 theta cosine theta plus, no, minus 2 sine 2 theta sine theta. Okay, and we need to do this where theta is pi over 4, right? So at pi over 4. Okay, so let's see. This would be cosine of pi over 2 sine pi over 4 plus 2 times sine pi over 2 cosine pi over 4 divided by 4 cosine pi over 2 cosine pi over 4 minus 2 sine pi over 2 sine pi over 4. And fortunately here, cosine of pi over 2 is 0. So this guy cancels. This is 0. And sine of pi over 2 is 1. So this becomes, get more paper. This becomes 2 cosine pi over 4 divided by negative 2 sine pi over 4 Both of these are radical 2 over 2. So the answer is -1. So that's the slope. And then to find the point, you just plug pi over 4 into the x and the y, right? So r is 2 sine 2 theta. And so what is x and y? X is r cosine theta and y is r sine theta. When theta is pi over 4, you get 2 sine pi over 2 times cosine pi over 4, and y you get 2 sine pi over 2 times sine of pi over 4. Again, these are ones, and these are radicals 2 over 2, so this is 2 times radical 2 over 2, and this is also 2 times radical 2 over 2, so this is radical 2, and so is this one. So the point is radical 2 comma radical 2, and the slope is pi over 4, so then the equation is y minus radical 2 equals the slope, -1, my bad, times x minus radical 2. And that's it, right? So you only need to know the formula, this formula over here. Let me go back. This is the formula to get, in general, the slope when you have a polar curve, right? That's the important thing to know. The rest of the procedure is essentially the same. Good. So what about arc length? So for arc length, you also need to know the formula. So let's take a look at that one. It's 27, okay, it says A. The numbering is not quite right, but 27 arc length problem. See, the formula for arc length is as follows. You go from alpha to beta, and is the derivative square the original function square. And the one we want to do is r equals theta square from 0 to radical 5. So let me go back to the page and show you the formula that I written already. So here is the formula. So it's the function square plus the derivative of the function square d theta, big square root of that from alpha to beta. So that's in general the function. So in this case, we want to do it from 0 to radical 5. And it's the derivative of, what is the derivative of theta squared? Is 2 theta. And what is the derivative of, the regular function square, so that's theta squared square. Right? And that's it. That's the part that you need to know, which is relevant. The rest is to do this integral, right? Now we're in the realm of solving integrals, in which we practiced before. So this is 4 theta squared plus theta to the 4th power. And here we're lucky that we can factor a theta square. And then take it out of the radical. And it's absolute value of theta, but theta is between 0 and √5, so it is positive. And that's fantastic, because now we can try a u substitution, right? We can say u is 4 plus theta squared. And du is 2 theta d theta. And so my new integral becomes the square root of u, and theta d theta is du over 2. And now u goes from, let's see, when theta is 0, u is 4. And when theta is radical 5, u is 9. Right? So that's not too bad. So it's a half the integral from 4 to 9 of u to the u to the power 1/2. So this is u to the 3 halves divided by 3 halves. That's multiplied by 2/3 from 4 to 9. Just go away here. And this is now 9 to the 3 halves divided by 3 minus 4 to the 3 halves divided by 3. And this is a reasonable answer. You don't need to simplify it. You could if you want. So the square root of 9 is 3. 3 to the cube is 27. The square root of 4 is 2 to the cube is 8. And 27 minus 8 is 19. But you can stop right here. That's perfectly fine, right? Good. So that's arc length of polar curves. And then we get to areas. So I'm also seeing it in the, pretty much that's a guarantee in a final exam. For the last 2 or 3, there's always been an area problem with polar curves. All right, so let's figure out one of these at least. And usually you have the graphs available, so that's a good thing. So let's do part B, for example. At least set it up, right? That's the hard part usually. So write it down as an integral. So for part B, we have here 2 regions. One is a circle, and I think both are circles, though they don't look like in the picture. So we're working on the right. Let me mark it. The right-hand side picture. And we have 2 curves, 2 circles, and we want to find out the area in between them. And we have this light blue one goes like here. Whoa. I'll try my best. That's 1 minus cosine. And then we have the other one, which is with the purple one. And for the purple one, we have, I'm only gonna do the relevant part, this one over here. Okay, and the area under the curve. So the purple one is cosine, okay? So the first thing you need to find out is where do they intersect, right? Because you're gonna integrate. So the area between 2 curves, let me switch to that. So if you have the area between 2 curves, have an, and you'll see my picture in just a moment. If you have 2 curves, this orange one, which is given by f of theta, and this green one, which is given by g of theta, and you want to know this area, then the area between the curves is given by 1/2 from this angle, alpha. So this is r equals alpha, and this is r equals beta. So from alpha to beta, and then it's the upper function square minus the lower function square. Okay, so this is not hard, and usually the integrals are not difficult. The hard part is to figure out from where to where, right? So now let's go back to our problem. So in our problem, that amounts to figuring out what is the initial angle. The initial angle seems to be, let me draw an arrow here, seems to be from here. This seems to be the initial position, right? And then we also have, well, it depends, right? Because here it's not clear. There's not an upper and a lower, right? So it seems like we're gonna need to break it down into 2 integrals. One that goes from this first horizontal direction to this direction, and then one that goes from that second direction to this new direction, which I'm gonna draw here, this green one. So from the horizontal to this one, and then from that one to the green one, vertical one, right? So we have to find this number, because on the first integral, we're gonna use the light blue graph. That's gonna be the outer graph, and there's no inner graph. And then from the second integral, we're gonna use the purple graph, right? Because it's the area under the curve of the purple graph. Okay? So first problem is, where do these two intersect? And they intersect where cosine t, which is the equation of the purple one, equals 1 minus cosine t, which is the equation of the blue one. So we have to solve for that and figure out what is the angle where that makes that happen. I'm going to change the t's to thetas, like we usually use here. All right? So let's do it. We need to figure out which theta makes this happen. And if you add theta to both sides, you get this. So that means cosine is 1/2. And which angle has a cosine of 1/2? That is 60 degrees of pi over 3, right? 60 degrees, which sort of matches our picture, right? So then the area we want is two integrals. One of them is from 0 to pi over 6, and the other is from pi over 6 to pi over 2. And the first one, the function we want to use is, so for the first one, we want to use the light blue one. So the light blue one is 1 minus cosine. And for the second one, we want to use the purple one, and the purple one is cosine. Right? Is that clear? So on one of them, let me put the arrow again that divided them. We have this one. And now we know it's pi over 6. And it makes sense with this picture. So for the first integral, we're going to find out what is this little area over here, the area that is below. This one over here. To find out that area that I'm shading right now, we need to use the blue graph, because it's going to be from the blue graph towards the center, from angle 0 to angle pi over 6. So from here to here, using the blue graph. And then to do the other part, to figure out the other area, this one, just a second. So for the second one, we want to do it from here, from pi over 6 to pi over 2. And then we're going to use the purple graph, and that's going to give us this little green area that I'm shading right now. Okay? So I'll show you the integrals. I've written them down already in the page. It's two integrals. So for this one is with the light blue, and this one is with the other one. Yes, Gerardo, what's up?
Can you use symmetry to solve this problem, or do you need to write both integrals down?
Good question. From the picture, I can't tell if both circles were the same size, then you could use symmetry and just do one of them, right? But I'm not sure. From the picture, I cannot tell if they're, because the picture is not up to scale, right? Because that purple circle seems elongated. It should be a regular circle. And this blue one does not even look like a circle, right? So in fact, I'm not sure the blue one is a circle. Maybe the blue one is, yeah, it should be a circle. Yeah, so I don't know. That's my, so maybe you could do it by symmetry. If you had a nice picture, maybe symmetry is a way to go. So we'll do it. If these two turn out to be equal, then symmetry would have worked. All right, let's finish it up.
Is there a way you can like know if they're like, if you can apply symmetry without looking at a picture?
Not really. No.
Okay.
But since you asked for it, let's actually try to figure it out. So we would need to do is we would need to draw these two, right? So what are these two equations? R equals cosine theta and R equals 1 minus cosine theta, right? And maybe you can draw them. And so, okay, let's see. Let's pursue your idea. So here are the two integrals that we set up, but Gerardo is asking if this could be done by symmetry, right? And for that, we would need to know these two graphs. So one of them was, I'll do it over here, looks like a circle, this one. And we have another one here. I think they're both circles. This is one minus cosine, and this is cosine. So let's try to identify what circles these two graphs are. If we have R equals cosine, right? So for this one, this is R equals cosine. If I multiply by cosine both sides, I would get R cosine theta equals cosine squared, right? But cosine squared is also R squared. So then we know this one is x, and this one is x squared plus y squared. So then I can complete the square. So I have 0 equals x squared minus x plus y squared. And then I complete the square. So this is, I add 1/4. So this is 1/2 squared equals x minus 1/2 squared plus y squared. So this is indeed a circle. It's a circle with center at 1/2 comma 0 and radius 1/2. So this is radius 1/2. Okay. Now let's try to do the same for the green circle. So for the green circle, I have that R is 1 minus cosine theta. So I'm going to multiply by R. So R squared is R minus R cosine theta. This is what I wanted to do. Let's see. This is it may not even be a circle. That's the thing, right? This one over here. I don't know if it's going to be a circle. So this is definitely X. But this one, I don't like it. That is just R. Let me see if I can do it a different thing. I can do maybe multiply by cosine. Then what do I do with no? Okay, so this is X. This is R squared is X squared plus Y squared. And R minus X. Now to get rid of R, that would be the square root of X squared plus Y squared. And I don't like this because that's not the equation of a circle. So maybe the green one is not a circle. That's the thing. All right.
Okay.
Yeah. Michael's saying isn't it pi over 3, not pi over 6? Yeah, you're right. A typo, right? I had gotten pi over 3. Yeah, you're absolutely right about that. There's pi over 3 over here. All right, so we still need to do these integrals. And maybe I mean, these are not hard, right? Maybe we just indicate it. So you need to expand these. Take the 1/2 out. So it will be 1 minus 2 cosine theta plus cosine squared. And the other one is cosine squared. And they're all straightforward. The only one that is a little bit hard is cosine squared. You need to use the half angle identity, right? So change cosine squared, change cosine squared theta to cosine 2 theta plus 1 divided by 2. That's the way you can deal with the cosine squares, and then everything should be easily integrable. So I'm gonna stop right there because I don't want to spend all the time, you know, doing things that we did before, right? We already talked about integrating trigonometric functions, in particular products of sines and cosines. So instead, I want to move it along and see other questions here. So so the rest of the questions, and we have like, let's go like 15 minutes. So we still have two chapters, 13 and 14. And I told you from the beginning, I'm not that stressed if we don't cover those with a lot of care, because we just had an exam about those. So I assume that those would be the ones that you are most familiar with. All right, so what are the kinds of things that you should remember that are important? And you should remember about how to get the length of a vector, right? How to do dot product and cross product. And let me summarize the important things here. So here is for about chapters 13 and 14, the kinds of things you need to know. You need to know how to add vectors and scalar multiply. That's easy, right? You just add component by component, or you multiply the scalar by everything. You should know how to do dot product. So if you can do it two ways, the easy way, which is just multiply their components. So it's V1 W1 plus V2 W2 plus V3 W3. If V has components V1, V2, V3, and W components W1, W2, W3. That's the easy way to do it, right? And the important relevant way is that V dot W is also magnitude of V times magnitude of W times the sine of the angle between them. Sorry, I'm saying it wrong. Cosine, my bad. Very important that you don't make this mistake. Where theta is the angle between U and W. V and W, yikes. Okay, so we use this to find out the angle between two vectors. So one way to find the angle between two vectors is to solve for cosine. So cosine would then be V dot W divided by the magnitude of V times the magnitude of W. And by the way, so the magnitude of V, you do it by doing the square root of V1 squared plus V2 squared plus V3 squared. Okay. That's how we do it. If it's in R3, if it's in 2 dimensions, then just like this, right? Just forget about the third component, and all the formulas work the same way. Excellent. So that's what you need to know about the dot product. Then we also have the cross product. Cross product. So V cross W is done by doing this determinant, right? And graphically, we know that V cross W, the magnitude of V cross W is the magnitude of V times the magnitude of W times sine. So this time it is sine. So notice how the similarities here, right? This dot product has cosine, cross product has sine, but cross product is another vector. Dot product is just a number. This is just a number. This is a different vector. And the V cross W is orthogonal. Is orthogonal to both V and W and follows the right-hand rule. So if you have vector V and vector W, you go from V to W with the right hand, and then V cross W will be perpendicular to both. Right? So there's a plane here that has V and W, and this guy is perpendicular to that plane, to the plane that has two, and it follows the right-hand rule. So if you do a little hand here that I cannot do, that goes from V to W, then the thumb points in the direction of the hand. So like this, right? Pointing in that direction. All right, so that's a quick summary of the chapter 13. Oh, and this also gets the area of, so that's another important thing about cross product. So the area of the triangle determined by vectors V and W is 1/2 of the magnitude of V cross W. And if you want the parallelogram, is without the 1/2. Okay, that is essentially a summary. And then we have for a vector equation, we have the tangent vector, which is just the derivative component by component, and the unit tangent vector when you divide by its magnitude. So let's take a look at the problems, see if there's anything we should review. I mean, we already reviewed. You can take a look at the videos. That's the other thing, right? So we already reviewed chapter 13 and 14, and we uploaded videos with that. I think, except there was one, maybe we're missing one day where my internet was down and I couldn't save the session. But other than that, you can check those. All right. I don't think we should be doing any of these, which we've done before. Let me just talk a little bit about this one here. When we have acceleration, velocity, how is that related, right? You need to remember that the velocity is the derivative of the position, and the acceleration is the derivative of the velocity, or if you want, the second derivative, right? To take the derivative and then take the derivative again. The second derivative is the acceleration. So in this problem, for example, you're given the acceleration. So to find the velocity, you need to do the antiderivative. You need to integrate the acceleration and then use the initial condition to find out the constants. Because when we integrate, there are constants there. And then once you have a velocity, you integrate again to find the position. I think most of you successfully did this problem in the last exam. I can't think, probably there was one or two of you that did not get it, but the rest of you did it correctly. So I think my feeling is that there will be a problem like that on the final exam. So make sure you review that. What else? And this part about arc length is the same as the one we did for parametric. So we did it only for two with X and Y earlier today when we reviewed parametric arc length of parametric equations. If you have X, Y, and Z, it's done the same way. Only now you have to do the derivative of the first square plus the derivative of the second square plus the derivative of the third one square. All right? It's similar, essentially the same thing. Okay, so I don't think I want to do any of these specifically unless you have a particular question. So I'm going to just stop right now. We have like 5 minutes. Maybe if there are any concerns, questions that you may have, I want to allow for some time for you guys to tell me, okay?
Yeah, Professor?
Yes.
When finding the angle in between the vectors, we could use either the cross product or the dot product, right?
Well, yes, except that I would use the dot product because the cross product is way harder, right?
Yeah.
So given the, yes, you could use both, but the best way is to use the dot product because dot product is easy to do, right? I mean, I can just invent a problem right now. In fact, let's do it. And we'll do it in 30 seconds or so. It's that easy. Let me show you. So say you wanted to do the, what is the angle between, find the angle. And I'm just invented it, so it won't be pretty numbers. between, let's say, the vector u, which is 1, 2, 3, and the vector v, which is negative 2, 4, 7, right? What is the angle between these two? Well, we know that u dot v is magnitude of u times magnitude of v times the cosine. So we just calculate everything right here. What is u dot v? Is 1 times negative 2, that's negative 2. 2 times 4, that's 8. And 3 times 7, that's 21. Then magnitude of vu, that's 1 squared, 2 squared, 3 squared. Magnitude of v, that's negative 2 squared, 4 squared, 7 squared. And then the cosine, right? So let's see, this is 21 plus 8, 29 minus 2, 27. This is 9, 10, 14, square root of 14. This is 16, and 4 is 20. 20 and 49, that's 69, cosine theta. So that means that cosine theta is 27 over the square root of 14 times the square root of 69. So what is the angle? Well, arc cosine of this number, right? And we're done, right? I mean, I know if you get a pretty number here that you know the cosine, you know, like radical 2 over 2 or square root of 3 over 2, then you can know the theta. Otherwise, you write it like this, the arc cosine function. All right? Anything else? Okay, very good, guys. So thank you very much. It was a pleasure having you. I know you guys made the best of our worst situation by regularly showing to these online lectures and following up with your work. I hope that you guys do well in the final exam. I'm pretty sure most of you will, and that you have an enjoyable summer after that. So pay attention to our announcement on Canvas, where I will tell you, I direct you where to go take the final exam. Go get the file and download it and work on it. All right. Anything else, guys? Okay, very good. So good luck, everyone. Study hard. It's a final push, and I hope you do well. See you guys.